Hello everyone, and thank you for tuning in to this workshop presented by Code Labs Academy. In this workshop entitled Precipitation Nowcasting with Machine Learning, we will talk a little bit about how climate is predicted and how machine learning is involved in these predictions. Nowadays, it is estimated that 90% of the climate predicted is correct for a 5 days prediction. However, this accuracy gets lower the further the time we're trying to predict. Therefore, an important question arises: how is climate predicted? Also, what are the techniques and the approaches used? So basically, there are two main approaches for climate prediction nowadays. The first one is based on using physics. It uses models that integrate measurable quantities such as pressure, the sky conditions, clouds movements, etc. These techniques are good for predicting the weather for the upcoming days or weeks. The second approach is the physics-free approach or the data-based approach. This approach uses only historical data gathered and use this gathered data to create a model that makes predictions. These models show good results in predicting the weather in the span of the upcoming 6 hours, or what we call weather nowcasting. In this workshop, we will be talking about the second approach, or the physics-free approach, which uses machine learning techniques to make predictions. So we have already seen how is climate predicted. In the remainder of the workshop, we will talk about the data used for climate prediction. We will also see the machine learning models with a special focus on the models that take an image as input data. We will also talk about the architectures and why they are important, and we will see a special architecture called UNet, which we will use in the following section of the workshop, which will be a coding session in which we will build a UNet-based model that allows us to make predictions. So let's talk about the data used for climate prediction. So there are mainly two types of data. The first one is radar and satellite image data. These data sets are used mostly to predict precipitation, winds movement, humidity. To exploit this type of data, we usually use convolutional neural networks. The second type of data is the tabular weather data, from which we have quantities that are measured or recorded, such as humidity, temperature, or precipitation. So each type from these two can be used to create powerful models. However, in this workshop, we will be working with image data and more specifically radar image data. Since we will be using radar images, let's talk about the machine learning models used for images. So, neural networks are one of the most widely used machine learning models nowadays. This model performs really well when fed tabular data. However, neural networks do not work well with images for the following reasons. First, the number of parameters explodes quickly. In this example, we have a 244 by 244 RGB image. This image is reshaped into an input vector of size 244 by 244 by 3. So we would need the same number of neurons in the input layers. This makes the neural network too large with too many parameters. The second reason is that the use of a neural network causes a loss of spatial information. Here in this image, for example, we wouldn't know that the two highlighted boxes are the edges of the cat's left eye. The third reason that we're going to mention is that neural networks are not translation variant. This means that a cat's face found in two different places in a picture is not handled the same way. So we wouldn't know that it's the same thing. So these problems are why we use CNNs or convolutional neural networks, which are let's say a more adapted type of neural networks to handle image data. CNNs allow us to extract features using convolutional layers. So these convolutional layers use filters. So let's say that a convolution is simply an element-wise multiplication of these filters used and the elements of the input. The result of these multiplications is then summed. The output of these convolutional layers are called feature maps. Sometimes the feature map tend to get really big, so we need to reduce their sizes. And to reduce the size of a feature map, we use pooling layers. So this operation results in a lower number of the features to learn. There are mainly two types of pooling operations. So the first one is average pooling. So in this one, we calculate the average of the elements covered by the size of the pooling layer. The second one is max pooling, in which we keep only the maximum value of the elements covered by the size of the pooling layer. So these were the two main concepts that are used in CNNs. However, since the appearance of CNNs, a lot of architectures were published. Sadly, a lot of people don't know why they're used or what is the importance of having these architectures. So there are lots of benefits to having architectures, from which we mention the following 4 reasons. First, they serve as guidelines to creating new architectures, because usually the people who create architectures try a lot of possibilities before reaching their architecture. So by following their architecture, we're sure to not repeat the same mistakes that they have and have a good template for us to go with for creating new models. The second reason is that these architectures are rich feature extractors. As people who create new architectures always aim to having better solutions to extract features, as feature extraction is one of the goals or one of the advantages of using CNNs. The third reason is that architectures are task-specific. Some of them are used for image segmentation, others for object detection, and so on. So this allows us to choose the best model for our use case. The fourth and the final reason is that most of the published architectures come with a pre-trained model. So the authors usually published the weights for their architecture or for their model after the training has been done. So this can be really useful, especially that these models have millions to billions of parameters and can take so long to train, especially if you're using your personal computer. Now let's talk about some of the most famous architectures. Starting with the LeNet model created by Yann LeCun, which is one of the first CNN model, and it has 60,000 parameters. The second model is AlexNet. This model is obviously bigger than LeNet. It has 60 million parameters. So we can clearly see how models are getting bigger and bigger. The third and final model that we're going to mention is VGG16, created by Karen Simonian and Andrew Zisserman from Oxford University. So this model has 138 million parameters. Now that we have seen some of the most famous architectures, let's talk about the model that we will be using, which is the model called UNet. So UNet is an architecture based on a fully convolutional network. This means that we don't have any fully connected layers in our architecture. So it was first used in medical image segmentation and achieved great results. So this results inspired researchers to extend it to other tasks in computer vision and use it on other types of image data. So in 2020, a research group from Google used a UNet-based architecture to create a model that does precipitation forecasting. So this goes to show that UNet is a very powerful architecture and has a lot of potential to achieve good results in a lot of tasks. So the reason UNet was given that name is because it looks like the letter U. Its architecture has mainly three different parts. So first we have the contracting or the encoder part, in which we follow a typical CNN architectures. So we only have a succession of convolutional layers and pooling layers. Next, we have the bottom part, which is called the bottleneck or the bridge. So this part is just a succession of convolution layers. But in this part, we are going to transit from the two main parts. We're going to make a transition between the two main parts of our unit architecture. So the third part is called the decontracting or the decoder part. So this model is composed of up-convolutions and convolution layers. So for those of you who don't know what up-convolutions are, don't worry, we will talk about them in the next slide. And for those of you who are familiar with autoencoders, this should look pretty familiar to you. So the difference is the addition of a concatenation that takes place in the decoder part. So we will be concatenating the output of the convolution layers from the contracting part with those from the decontracting part. So this adds some spatial information to the second part or to the third part, because this simple modification enhances the transfer of spatial information between these two parts, and it also allows us to enhance the resolution of the output. Now we will see how this model behaves. So basically we start with an input image and we will apply a bunch of convolution operations followed by max pooling. So this is the encoder part, and we repeat this operation 4 times. After that we reach the bottleneck area, in which we follow a succession of convolutions. Then we have an up convolution operation which takes us to the third part, which is the decontracting part or decoder part, in which we have concatenations, as you can see with the gray arrows, and we have up convolutions and convolution layers. And we notice that in the last layer we have a 1x1 convolution layer, just so we can get the output image. Now let's talk about up-convolution. So up-convolution is sometimes wrongly called deconvolution. So basically up-convolution is a layer in which we do the opposite of what pooling does. So in pooling we will be halving the input. This is the general use case. However, in up-convolution we will be doubling it. So there are 2 methods to do up-convolution. So the first one is called the dumb method. It's called upsampling, which is somehow the dumb method, because we will be simply copying the lines and the rows and doubling them. This method has no learnable parameters, therefore it's called the dumb method. The second one is to use an operation called convolution transpose. So this method is equivalent to an upsampling followed by a normal convolution with a filter, and obviously the filter will be learned, therefore the second approach has learnable parameters. Now let's jump to the coding session of this workshop. So the coding session will be mainly divided into 3 parts. In the first one we will see data handling. The second part we will create our model, and the third part we will be using a pre-trained model called RainNet to make predictions for a specified span of time. Now that we have seen the theoretical aspect of the workshop, let's start with the coding part. So first we have to mount the drive. You can do this with these 2 lines of code, but I have already done it, so feel free to do it on your own. Now for getting our data. For the data we will be using the German open weather data. And first, before using the data, we will be first downloading the RadLib library. So this is a library specialized in managing radar images. So we install it using this command. As you can see, the library is being installed for the moment, so we just have to be patient with it. Alright, as you can see, the requirements are already satisfied for most of the packages, and that's because I have already used the library. Now, since we have managed to install the library, let's import it. So we can simply import it using this command. We have successfully imported the library. Now, let's start with downloading the data. So I have imported a few libraries here that are useful for what's coming, for the piece of code that is coming. These are the 4 libraries that we will use for now, alongside the radlib library. So first, we will create a function that downloads an image, a radar image, given its timestamp. So we will be just executing the code for this function. Feel free to pause and check the code on your own, but it isn't that important. Another part of downloading the data is that for our model, we won't only be using one radar image, so we will create a function that downloads the previous 3 images. So we will give it a timestamp, and it will download the 3 previous images to that timestamp, which gives us a total of 4 radar images. So we can execute this cell once again, and after that we will go and check how we can download our data. So we will be simply calling the function that we created. Alright, perfect. So the 3 elements that you can see right here are the timestamps of our radar images. Now what we can do is that we can print the shape of our y-latest, just so we would know how many examples you have in it. And what we can also do is to use the method viz.plot ppy to plot the radar images that we just downloaded. Alright, as you can see right here, these are the radar images that we just downloaded. There are 4 images like we have seen, so we have one which is the latest, and we used the download data method to get the 3 images that were previously taken after the latest one, which is a total of 4 images. So now that we have these 4 images, let's start with creating the model, because we already have seen the data that we have and we know what we are dealing with. So first we will be importing some classes, which are some classes from TensorFlow. So we will be using TensorFlow for creating the model. So we can just run these cells to import these. Alright, so importation has been done successfully. Now for the model creation, we'll be following a what I call a block-based approach for implementing it. So basically here what I'm doing is that I'm trying to instead of using a function that creates each operation in our model independently, for example coding convolution by convolution layer, then max pooling layer, I'll be grouping them following the architecture that we saw. So the main building block is called a convolution block, which is a 2D convolution followed by a ReLU activation, and then we repeat those two, so a convolution followed by a ReLU activation. So you can find this convolution block in all of UNet. You can find it the contracting part, the bridge, and the decontracting part. The second building block is a encoder block. So you can notice that in an encoder block we have a convolution block followed by a 2D max pooling. And finally, as you guessed it, since we have an encoder block, we will have a decoder block. So this is simply a conv2D transpose, or you can use, like I said in the theoretical part, you can use upsampling if you want. It is up to you. Followed by concatenating it from a concatenation from the of the result of the encoder part with the decoder part, and finally we have a convolution block. So this is basically it for the building blocks that we need. Now let's try to use these building blocks to build our unit model. So first we will create a function and we will define an input shape. You can feel free to change this input shape depending on your use case. So the first thing that we're going to use or we're going to implement is the encoder part. So this is, like I said, basically a succession of encoder blocks. Here we can notice that the encoder block has been written wrong, so I'm just going to go ahead and update this real quick. All right. Yeah, now that we have the encoder, let me just continue and then I'll get back to it. The second part of our unit architecture is obviously the bridge part, which is simply a convolution block. After that, we will have the decoder part of our unit architecture, which is a succession of 4 decoder blocks. Now that we have our 3 parts of our architecture, we have one more step, which is to add a 1x1 2D convolution layer just to give us the output in the form of an image. And of course, we have to use all of these blocks to create our model that has inputs variable as an input and outputs variable as an output. And like I said, I just need to modify this because it was written incorrectly. Yeah, and this should be pretty much it. So we will run this cell and it looks like everything is so far so good. Now, since we have built our model, as you know, training such a model can take days or even weeks depending on your personal computer. If you're not using any supercomputer, if you don't have access to some cloud solutions that you can use to train your model. So what we're going to do is we're going to use a pre-trained model, which is the RainNet model. So the first thing is that we will clone the repository that has the model. So this can take some time. All right, so it is done. It didn't take a lot of time. Now, what we can do or what we need to do is to download the weights, which, like I said in the theoretical part, one of the main advantages of having an architecture is that we can download the weights simply. So we download the weights, and this should also take some time. All right, perfect. So the weights have been downloaded. Now that we have downloaded the weights, let's just go ahead and do a little sanity check to see if everything is in its right place. All right, perfect. So we can see that we have the RainNet model right here, which is in this file, and we have the weights right here. So far, so good. So let's continue. Now, what we will be doing is that we'll be just running our model, or we'll be creating our model from the RainNet, and we'll be loading the weights. So we run this real quick. Perfect. So we added a little model.summary, so just we can check the different layers if we want. But this is basically these are basically the layers that are in our model. So you can check the number of parameters. You can also see how many of them are trainable. So in this case, all of them are trainable. Now that we have created our model, let's go to the next part. So basically in this part, this isn't relevant to our workshop, but I'm just doing some, I'm using some functions that do some data pre-processing and post-processing. Because basically what you should know about the data that we downloaded from the German open data for radar images is that the images they have are a 900 by 900 images. However, in RainNet there is a constraint which says that we should have we should have input images that have a size that is that can be divided by 2 to the power of n plus 1, with n being the number of pooling layers. Because like like we saw in the aspect, in the theoretical aspect, the pooling layers will have the images. So we would need a size that can be halved as many times as what the model dictates. Alright, so feel free to pause the video just so you would check these functions. And of course, we shouldn't forget to run the cell. Alright, perfect. Now what we will do is that we will use a simple prediction function in which we will do some pre-processing. We do the prediction, and one thing that you should notice is that once we have a prediction, we add that prediction to the input data, just so that the first predicted image is used to make the second prediction, the second is used to make the third prediction, and so on. So this sort of gives our model the ability to use the data predicted to predict the future data images. And of course, we shouldn't forget to run the cell. Alright, so far so good. Now what we will do is that we will make the actual prediction using the model we created and the data we downloaded. So we run the model. This sometimes takes a few minutes, so we will just wait for it until it is done. Perfect, now it is done. Now what we will do is that we can check the shape of the model. So we have predicted 24 radar images, and they have the size 900 by 900, which is the size of the data that we had as an input. Now what we can do is that we can plot these images, and one more thing that we're going to do is that we're going to save these images after plotting them. And we will see why we saved these images in the next cell. So we will use the same method that we used in the beginning of the code, and we will be just saving the images using these functions. And of course, we will be also saving the names of the images that we saved. We run this cell. And we wait for the results to show up. As you can see, these are the images. The images that are showing up are the predictions that we have from our code. Let's take a look at them. So you can see the evolution that is happening in the radar images. It might not be that apparent, but if you compare like the last with the first one, you will definitely see the changes. Or one more, let's say one elegant way of noticing the differences is what I'm going to do right now. So what I'm going to do will be somewhat like I said, an elegant way of visualizing the images. What we will do is that we will import the library image.io, and we will create a GIF or a GIF, depends on how you like to call it, from the images that we just predicted. So we will run this cell. Perfect. And now what we can do is that we can observe this image. As you can see, when we were scrolling earlier, we didn't notice the differences, but now it is pretty apparent how the evolution is taking place in the images that we just predicted.